The Massive Multitask Agent Understanding (MMAU) benchmark is a comprehensive evaluation framework for assessing the capabilities of large language models (LLMs) as human-like agents. It features 20 offline tasks across 5 diverse domains: Toulouse, Directed Acyclic Graph, DAG, QA, Data Science and Machine Learning Coding, Contest-Level Programming, and Mathematics, covering essential capabilities like understanding, reasoning, planning, problem-solving, and self-correction. This benchmark eliminates the need for complex environment setups, ensuring reliability and reproducibility. The authors test 18 representative models, offering in-depth analyses of their performance, including domain-centric, capability-centric, and overall performance. The results are aggregated from all 20 tasks in MMAU, with detailed per-task evaluations available. By introducing MMAU, the authors aim to enhance the interpretability of LLM agents' performance, shedding light on their capabilities and limitations. The Massive Multitask Agent Understanding (MMAU) benchmark is designed to evaluate the fundamental capabilities of large language models (LLMs) as intelligent agents. It assesses capabilities like understanding, reasoning, planning, problem-solving, and self-correction across 5 domains. The benchmark includes over 3,000 distinct prompts, spanning 64 subjects and 5 domains, to evaluate LLMs in a disentangled manner. The evaluation of 18 models on MMAU, encompassing both commercial and open-source models, provides a comprehensive framework for understanding the strengths and limitations of LLM agents. This includes evaluations from specific application scenarios and fundamental capabilities, ensuring a unified and straightforward analysis on a static dataset. The MMAU benchmark aims to complement interactive evaluations by addressing issues related to instability. Additionally, the dataset and scripts for evaluation are released, setting a new standard for performance assessment in the AI landscape. The significance of MMAU lies in its ability to offer a stable and easy-to-use benchmark for a wide range of tasks, making it a valuable contribution to the field. The authors introduce MMAU, a comprehensive benchmark designed to evaluate the core capabilities of large language model (LLM) agents. As shown in Table 1, MMAU offers unique features and advantages compared to existing benchmarks, providing a disentangled evaluation of various capabilities, including understanding, reasoning, planning, problem-solving, self-correction, and multimodal grounding. In contrast to existing benchmarks, MMAU focuses on fundamental and essential capabilities for LLM agents, offering a more comprehensive evaluation of these capabilities in a disentangled manner. The authors define the capability definitions and key tasks used to evaluate them, including complex instruction following, user intent understanding, statistics parsing, and visual grounding for understanding. To evaluate reasoning and planning capabilities, the authors introduce the planner shift task, which decomposes the solution generation into 2 stages: a planner model generating a high-level plan, and a solver model solving the problem. This approach isolates the planning and reasoning processes from problem-solving. The solver shift task, similar to planner shift, varies only the solver models to reflect differences in problem-solving skills. The MMAU benchmark provides a range of tasks designed to produce decoupled metrics over the core capabilities, allowing for a more comprehensive evaluation of LLM agents. These tasks enable the assessment of LLM agents' abilities in understanding, reasoning, planning, problem-solving, self-correction, and multimodal grounding, providing a nuanced understanding of their strengths and weaknesses. The Multimodal Abstraction and Understanding (MMAU) dataset is designed to assess a language model's capacity for understanding and applying knowledge across various domains. This dataset comprises data from in-house Toulouse, Kaggle datasets, Code Contest, and Deep Mind Math, encompassing tasks such as Toulouse, DAGQA, DS and ML coding, contest-level coding, and math tasks. In the Toulouse task, the model is evaluated on its ability to adhere to the standard Toulouse protocol and generate appropriate function calls based on user queries. The dataset includes single-step and multi-step Toulouse conversations, with some requiring parallel tool calls. For evaluation, the model's response is compared to the ground truth function calls and parameters. The DAGQA task assesses the model's ability to select and order a sequence of tool invocations from multiple choices. This task is derived from the multi-step Toulouse examples, where the model must identify relevant tools and deduce correct dependencies between them. The Toulouse self-correction task evaluates the model's capability to correct errors. Two classes of errors are simulated: temporary errors, where a tool is temporarily unavailable, and incorrect calls, where the previous tool call or response contains an error. The model is expected to retry with the correct call, and its performance is measured by exact match accuracy against the ground truth. This section of the research paper focuses on the evaluation of data science and machine learning tasks, specifically in the context of code generation and question answering. The authors leverage the Meta-Kaggle code dataset and curate 28 Python notebook-style conversations, with 123 conversation turns, to assess the model's capabilities. The evaluation settings include 4 tasks: end-to-end code generation in QA, code generation in GPT-4 QA, QA from Oracle code, and DS and ML self-correction. These tasks aim to gauge the model's overall capability, code generation capability, textual and visual understanding proficiency, and self-correction ability, respectively. The authors also explore contest-level coding problems, selecting 261 problems from the code contests dataset. The tasks in this setting include end-to-end standard, planner shift, solver shift, problem parsing, and code contest self-correction. These tasks evaluate the model's ability to solve coding problems, plan and problem-solve, predict outputs, and self-correct, respectively. The metrics used to evaluate the model's performance include QA accuracy, and match accuracy. The authors also provide examples of conversation turns, such as the one shown in Figure 5, which demonstrates the model's ability to generate code and answer questions. Furthermore, the authors analyze the correlation between different columns in the admission.csv dataset, identifying the 2 variables with the highest correlation. The Python code snippet provided computes the correlation matrix and masks the upper triangular portion to visualize the results. Overall, this section presents a comprehensive evaluation framework for data science and machine learning tasks, highlighting the model's strengths and weaknesses in code generation, question answering, and problem solving. This research paper presents a comprehensive evaluation of 18 models on the Multimodal Arithmetic Understanding (MMAU) benchmark. The models are assessed across 4 domains: Toulouse, data structures and algorithms, DS and ML, code contests, and mathematics. The results indicate a significant performance gap between API-based commercial models and open-source models across all evaluation domains. In the Toulouse domain, GPT-4o and GPT-4 Turbo demonstrate the highest performances, with GPT-4o achieving a 69.33% success rate. In the DS and ML domain, GPT-4 Turbo leads with a 79.38% success rate. For code contests, GPT-4o and GPT-3.5 Turbo are the top performers, with GPT-4o achieving a 31.80% success rate. In the mathematics domain, GPT-4 Turbo and GPT-4o lead with success rates of 38.57% and 53.40%, respectively. The paper also introduces several tasks to assess the model's planning, problem-solving, and understanding capabilities in the mathematics domain. These tasks include E2E Standard, Planner Shift, Solver Shift, and Comprehend Plus. The evaluation results highlight the varying strengths and weaknesses of the models in these different tasks, providing insights into their capabilities and limitations. Overall, this page presents a detailed analysis of the MMAU evaluation results, shedding light on the performance differences between commercial and open-source models and offering insights into the model's capabilities in various domains and tasks. The table presents a capability-centric evaluation of various language models, focusing on their performance in problem-solving, self-correction, understanding, reasoning, and planning tasks. The GPT-4 family consistently outperforms other models, particularly in math and contest-level coding tasks. Claude 3 Opus and Gemini 1.5 Pro also demonstrate strong capabilities. Among open-source models, Hermes 2 Pro Mistral 7B shows significant Toulouse performance. Models that do not support tool use, such as Mixtral 8x22b Instruct v0.1, perform well in math and DAGQA tasks, highlighting their reasoning and planning capabilities. The Llama 2 family struggles with challenging coding tasks. In terms of specific capabilities, GPT-4o significantly outperforms other models in understanding tasks, demonstrating its superior ability to handle long contexts and complex user instructions. For reasoning and planning, the GPT-4 family shows the strongest performance. The performance gap in problem-solving tasks is not significant, suggesting that this capability may be universally achievable among different models. However, there is a significant gap in self-correction capabilities, with most open-source models lacking the skill to reflect on and correct their own errors effectively. This highlights the need for further research and development in this area. The Massive Multitask Agent Understanding (MMAU) benchmark is a comprehensive test bed designed to evaluate large language models (LLMs) based on both application scenarios and fundamental capabilities. It decomposes capabilities beyond standard evaluation benchmarks, providing granular insights into the strengths and limitations of these models. The MMAU benchmark includes 20 tasks that assess various capabilities, revealing different levels of difficulty for models to achieve. Evaluation results show that problem-solving capabilities exhibit a smaller performance gap among models, suggesting it's a universally achievable capability. However, self-correction capabilities present a significant challenge, with a notable performance gap observed among models, and many open-source models lacking effective self-correction skills. Strong models, such as the GPT-4 family, demonstrate balanced performance across all capabilities, indicating improvements in one area likely enhance performance in others. The paper also observes that larger models are not always better. For the Mistral AI models, performance gains are consistently observed with increasing model size across domains. However, this trend does not apply to the Llama 2 families. In code-related domains, all size variants of Llama 2 perform poorly. Surprisingly, in the DAGQA domain, the Llama 27b model performs better than its larger counterparts. The MMAU benchmark has limitations and areas for future work. It does not encompass all possible domains relevant to LLM agents, such as interactive environments, which are critical yet challenging. Future iterations of MMAU should aim to include interactive tasks to provide a more holistic evaluation. This expansion will require the development of reliable, stable, and user-friendly interactive environments. Moreover, as we expand to include more domains, it will be essential to incorporate additional capabilities such as retrieving, memorizing, sequential decision-making, etc. The paper emphasizes the importance of considering potential ethical concerns and negative societal impacts in research on LLM agents. It is crucial to ensure that these evaluations do not inadvertently reinforce biases or propagate harmful content. The paper presents a thorough examination of advanced deep learning techniques for anomaly detection in high-dimensional datasets. Specifically, the authors propose a novel framework that integrates the strengths of autoencoders and one-class support vector machines to identify anomalies in complex systems. The authors first provide an in-depth review of existing anomaly detection methods, highlighting their limitations and trade-offs. They then introduce their proposed framework, which leverages the feature learning capabilities of autoencoders to extract meaningful representations of normal data patterns. The one-class SVM is subsequently used to establish a decision boundary that distinguishes between normal and anomalous data points. The authors also propose a novel loss function, which combines reconstruction error and classification loss to optimize the performance of the framework. This approach enables the model to learn a robust representation of normal data and effectively identify anomalies. Experimental results on multiple benchmark datasets demonstrate the superior performance of the proposed framework compared to state-of-the-art methods. The authors also provide a comprehensive analysis of the results, highlighting the benefits of their approach in terms of detection accuracy, robustness, and computational efficiency. Finally, the authors discuss the limitations of their approach and identify areas for future work, including the need for further exploration of the proposed framework's applicability to real-world applications and the development of more robust evaluation metrics for anomaly detection. In this paper, we present a comprehensive list of advanced methodologies and algorithms for optimizing quantum computing systems. The primary focus is on enhancing the efficiency of quantum information processing through novel approaches in quantum error correction, entanglement generation, and quantum gate optimization. Our research introduces an innovative quantum error correction code that significantly reduces the error rate in quantum computations. This code leverages the principles of quantum entanglement and superposition to detect and correct errors in real time, thereby enhancing the reliability of quantum computations. Furthermore, we propose a new method for generating high-fidelity entangled states, which are crucial for quantum teleportation and quantum cryptography. This method utilizes a combination of quantum gates and carefully controlled environmental conditions to achieve unprecedented levels of entanglement fidelity. Additionally, our study explores various quantum gate optimization techniques aimed at minimizing the number of quantum gates used in complex computations. By reducing the gate count, we can decrease the overall computation time and improve the system's performance. The paper also discusses the limitations and assumptions of these methodologies, as well as potential avenues for future research. Overall, this work contributes to the ongoing efforts in advancing quantum computing technology and overcoming its current challenges. Advances in large language models have led to significant improvements in their capabilities, but also highlighted their limitations. A study by Jimenez et al. 2024 evaluated the ability of language models to resolve real-world GitHub issues, while Valmikam et al.'s work, 2022, emphasized the challenges these models face in planning and reasoning about change. The GPT-4 technical report by Acyclic et al. 2023 provides a comprehensive overview of the GPT-4 model, which is further complemented by OpenAI's GPT-4o model. The GPT-4o model is a variant of GPT-4 designed for optimal performance in a wide range of tasks. In addition, the Gemini model family has been developed to unlock multimodal understanding across millions of tokens of context. Specifically, Gemini 1.5, developed by Reed et al. 2024, aims to achieve this goal. The Gemini model family is also discussed in a separate work by Gemini Google et al. 2023, which introduces a family of highly capable multimodal models. These advancements and developments highlight the capabilities of large language models in resolving real-world issues, planning, and reasoning. However, they also underscore the challenges these models face, particularly in planning and reasoning about change. The Gemini model family's focus on multimodal understanding and the GPT-4o model's optimal performance in various tasks demonstrate the ongoing efforts to improve the capabilities of large language models. The page presents a comprehensive list of research papers and technical reports on advanced language models and their applications. It includes works by various authors, focusing on Mixtral of experts, Mistral 7b, and other models. The page also discusses the methodologies and key findings of these studies, highlighting novel ideas and significant contributions to the field. The MMAU dataset, outlined in Table 4, comprises a diverse range of tasks, including Toulouse, sports, health, and location, each with distinct prompt and answer types. This dataset is evaluated using a suite of models, listed in Table 5, which includes both commercial and open-source models, distributed across multiple GPUs to facilitate efficient processing. The Toulouse task, a key component of the MMAU dataset, employs a data construction protocol that involves user queries, agent responses, and function calls to generate accurate predictions. This protocol is designed to provide a comprehensive understanding of the task, enabling the development of effective models. The evaluation process for the MMAU dataset involves a rigorous protocol to ensure accurate comparisons between predicted and ground truth parameter values. This process includes string normalization, which eliminates variations in formatting, and example-specific match rules, which account for task-specific nuances. These steps enable a precise assessment of model performance, facilitating the identification of strengths and weaknesses. The use of multiple models, including commercial and open-source options, allows for a comprehensive evaluation of the MMAU dataset, providing insights into the capabilities and limitations of each model. The distributed processing across multiple GPUs ensures efficient processing, enabling the analysis of large datasets and facilitating the development of accurate models. This research paper discusses various evaluation protocols for assessing the capabilities of large language models, LLMs, in different problem-solving tasks. These protocols include Data Construction Protocol for DAG-QA, Self-Correction Tools, Contest-Level Coding, and Problem Parsing. Each protocol is designed to test specific aspects of LLMs such as reasoning, planning, and code generation. The data construction protocol involves formulating a task as a multiple-choice question where the agent must choose the appropriate plan from a list of potential functions. The task input includes a description of the task, a list of potential functions, an enumeration of all possible plans, and the task input. The self-correction tools protocol encourages models to retry by prepending a specific system message to the user's first turn message. This message prompts the model to be concise and provide a response in the requested format. The contest-level coding protocol evaluates ILM's ability to generate Python code solutions for problems from the code contests dataset. The agent is given a detailed description of the problem with public test examples and basic instructions on code formatting. The generated code solution is considered correct only if all test cases are passed. The score is used to measure the performance, which is the percentage of problems solved by generating 5 solutions per problem. The problem parsing protocol assesses the agent's ability to directly infer the desired output for an unseen test case given the problem description and public test examples. The unseen test case is selected from the union of private test cases and generated test cases. The answer is compared with the ground truth output to derive the accuracy over the entire dataset. Finally, the PlannerShift and SolverShift protocols evaluate the planning and problem-solving capabilities of LLMs in code generation tasks. In PlannerShift, the planning capability is assessed by fixing the solver to be the same strong model and generating one plan with temperature 0. In SolverShift, the problem-solving capability is evaluated by freezing the planner and letting LLM agents generate 5 code solutions with temperature 0.3. The capabilities of LLM agents in tool use, problem-solving, understanding, reasoning, planning, and self-correction are assessed. For tool use, agents are tested on their ability to execute tools and generate code. In problem-solving, they are evaluated on their capacity to solve problems using tools and provide step-by-step solutions. Understanding is measured through the agent's ability to answer questions about the input context and provide explanations for their answers. Reasoning is tested by requiring the agents to reason about the input context and provide evidence for their conclusions. Planning is assessed by asking the agents to generate plans to solve problems. Self-correction is evaluated by collecting error messages from failed attempts at solving problems and using these as feedback to encourage the agent to retry. A subset of math problems is curated based on difficulty level, and a new set of more complex math problems is created while retaining the same underlying mathematical constructs. The final set of problems is ensured to be valid and have the same ground truth answers as the original set. The page presents 2 prompt templates for tool use and directed acyclic graph, DAG, reasoning, respectively. For tool use, the concrete prompts are generated by the model to transform tool definitions, predicted tool calls, and tool results into the concrete prompt. This process is demonstrated in figures 10, 11, and 12. In the DAG reasoning prompt, the task is to choose an appropriate plan with its associated set of tools to accomplish a specific task. Each tool's functionality is described using Open API schema notation. The prompt includes various scenarios such as tools operating concurrently without interdependencies, one tool requiring the output from another, and tools operating in parallel followed by a subsequent tool that requires outputs from both. The prompt also includes a compilation of all available tools in JSON format, possible plans, and the task input. The respondent is asked to elaborate on their thought process and reasoning, and strictly end the reply with, chosen plan. N, where N is an integer number of the selected plan. The second listing for DAG planning prompt is similar to the first, with the same task of choosing an appropriate plan with its associated set of tools to accomplish a specific task. The prompt again includes the compilation of all available tools, possible plans, and the task input, with the same request for elaboration on thought process and reasoning, and the strict ending format for the reply. In data science and machine learning code generation, a task input is presented where users require assistance in analyzing data and answering multiple-choice questions based on the analysis. The input consists of a Jupyter Notebook file containing code cells and markdown cells, accompanied by a list of data files used in the notebook. This notebook represents a conversation between a user and an assistant, where the user asks questions, provides clarification, and the assistant analyzes data, offers insights, and responds to inquiries. The task demands the generation of an appropriate code cell to address the user's request in the last markdown cell of the notebook and subsequently answer multiple-choice questions based on the execution results of the code cell. An example is provided, where the user requests to visualize the frequency of Pokémon by their primary type. The input consists of a Pokémon dataset in a CSV file, and the notebook contains code cells and markdown cells demonstrating the conversation between the user and the assistant. The notebook structure is defined, comprising cells containing metadata, source code, and execution counts. The language used is Python 3.11.8, and the notebook format is NB format 4 with a minor version of 5. The task requires appending an appropriate code cell to the notebook to address the user's request and then answering the multiple-choice questions based on the execution results. The methodology for creating a bar chart to visualize the frequency of Pokémon by their primary type is discussed. It begins with the importation of necessary libraries, including Matplotlib for plotting. The code utilizes the _value_counts method to determine the frequency of each primary type and plots this data using a bar chart. The chart is titled, Frequency of Pokémon by Primary Type, and includes labels for the z-axis, primary type, and y-axis, frequency. The code concludes with a call to "plt show" to display the chart. This section highlights the technical steps involved in creating a visual representation of the data, demonstrating a clear understanding of data visualization techniques. In data science and machine learning, the choice of libraries and packages is crucial for efficient and accurate task execution. Importing necessary packages in code cells is essential to ensure robust and generalizable code. For instance, approved math packages like NumPy provide fundamental mathematical functions, while data manipulation and analysis rely on libraries like pandas. Visualization packages such as Matplotlib enable effective data representation, facilitating insights and pattern recognition. When it comes to data science and machine learning prompts, execution feedback and code contests are vital components. These elements enable the evaluation of code performance, debugging, and optimization. Moreover, they facilitate the development of competitive coding skills, promoting innovation and excellence in the field. The incorporation of approved packages is critical, as it ensures that code is reliable, efficient, and adaptable to diverse problem domains. By leveraging these packages, data scientists and machine learning practitioners can focus on developing novel solutions, rather than reinventing fundamental functionality. In summary, the judicious selection and implementation of libraries and packages are essential for successful data science and machine learning endeavors. By emphasizing the importance of approved packages and robust coding practices, researchers and practitioners can accelerate their workflow, improve code quality, and drive innovation in the field. In the code contest's problem parsing prompt, an AI is tasked with understanding complex instructions and applying logical reasoning to solve a problem. Given a problem description and a relevant example input, the AI must deduce the correct answer. Its response consists of two sections: thoughts, which reflects its understanding of the problem and test case in 5 sentences or less, and answer, which provides the solution to the problem. The code contest's planner shift prompt requires the AI to devise a structured and executable plan to solve a problem. This plan outlines logical steps to address the problem, breaking down complex processes into manageable actions that can be easily translated into executable code or functions by a language model. The plan should be simple, focused, and avoid unnecessary complexity to ensure ease of implementation. The format for the planner shift prompt consists of a problem description followed by the generated plan, which clearly outlines the steps needed to solve the problem, making it easy for a language model to implement the solution. These prompts are designed to evaluate the AI's ability to understand complex problems, apply logical reasoning, and generate executable solutions. The concise format and clear instructions enable the AI to focus on the problem-solving task, while the planner shift prompt allows for a more detailed and structured approach to solving the problem. Artificial intelligence is tasked with two distinct code generation and problem-solving exercises. In the first task, AI generates Python code to solve a specific problem, denoted by "problem", using a provided solving plan, "plan". The generated code must be robust, general, and correctly address the problem goals while adhering to given rules and constraints. It should be self-contained, executable ArXiv, and include necessary module imports, proper variable initialization, and constraint handling. The output structure consists of defined functions "f1", "f2", etc., and a main execution block. Input reading and parsing, as well as output printing, must follow prescribed formats. In the second task, AI demonstrates human-like comprehension capabilities by solving a mathematics-focused problem. When presented with a problem, "problem", AI deduces the correct answer, "answer". The response format consists of concise thoughts, "thoughts", reflecting AI's understanding of the problem, followed by the derived answer, "answer". The thoughts section should not exceed 5 sentences, and the overall response must adhere to the specified format. Both tasks emphasize the importance of carefully following provided guidelines and formats to ensure accurate and effective problem solving. The ability to generate robust code and demonstrate human-like comprehension capabilities highlights the potential of AI in solving complex problems. The evaluation and planning aspects of mathematical problem solving are crucial for accurate solutions. It begins with step-by-step thinking, emphasizing the importance of verifying answers against ground truths, considering mathematical theorems. This involves a structured prompt that includes a question, an answer, and the ground truth, requiring a response indicating whether the answer is correct or wrong. Following this, planning is essential, involving the breakdown of complex processes into manageable actions. Each step should be straightforward and easily translatable into executable calculations or functions by a language model. The authors present additional evaluation results for domain-centric tasks, adhering to the standard setup used in the field. Specifically, they utilize the evaluation results of E2E standard tasks as domain evaluation results for contest-level coding, DS and ML, Math, and DAGQA. For toolus, they report the weighted average of single, parallel, and multi-turn multi-tool use tasks, as shown in Table 2. The Math task evaluation results, presented in Table 7, compare commercial models and OS models. GPT-4o achieves the highest accuracy, closely followed by GPT-4 Turbo and Gemini 1.5 Pro. The detailed results for the tool use datasets are reported in Table 8, noting that the distractor datasets contain 2 additional samples, which will be removed in future versions. Table 9 presents the evaluation results on data science and machine learning tasks, assessing E2E code generation and QA, code generation with GPT-4 QA, QA from Oracle code execution, and DS and ML self-correction. GPT-4o achieves the highest accuracy across all settings, closely followed by GPT-4 Turbo, highlighting its robust code generation and QA capabilities. The authors compare the performance of various models, including GPT-4o, GPT-4 Turbo, Gemini 1.5 Pro, Claude 3 Opus, and others, using the evaluation results. They also report the limitations of certain models, such as Command R and Command R+, which do not support multi-step tool calls. Overall, the results provide insights into the strengths and weaknesses of various models in domain-centric tasks. The evaluation of AI models in data science and machine learning, as well as contest-level coding, reveals significant performance differences. In the data science and machine learning domain, GPT-4o and GPT-4 Turbo excel, with GPT-4o showcasing exceptional question-answering skills, achieving 88.60% in QA from Oracle execution. However, its code generation capabilities are less effective compared to GPT-4 models. In contest-level coding, GPT-4o and GPT-4 Turbo demonstrate the highest performance, with GPT-4o scoring 31.80% in the end-to-end standard category, indicating its aptitude for complex coding tasks. Mixtral 8x22BV0.1 is identified as having the best performance among open-source models, highlighting its potential in real-world applications. The paper discusses limitations and future work, emphasizing the need for more comprehensive evaluations and a better understanding of model strengths and weaknesses. The analysis on page 26 underscores the superior performance of GPT-4 Turbo in achieving better results compared to other models. It highlights the significant performance variations among models on tasks like problem parsing, indicating the intellectual challenge of understanding contest problems. The evaluation focuses on understanding and planning capabilities, showcasing how models like GPT-4o and GPT-4 Turbo excel in E2E standard tasks but struggle in PlannerShift and SolverShift, possibly due to the limitations of their fixed solver planner. This page underscores the importance of powerful planning and reasoning structures for solving algorithmic challenges, particularly in the contest-level coding domain. The proposed dialogue management system effectively handles exceptions and errors through its ability to recognize temporary errors and retry calls, as well as correct mistakes based on explicit feedback. Figure 7 illustrates a retry example, where the assistant recognizes a temporary error and retries the call, successfully completing the task. This showcases the system's capacity to recover from temporary errors. Figure 8 presents a self-correction example, where the assistant receives feedback regarding an erroneous call, corrects its mistake, and provides the correct response to the user. This highlights the system's ability to adapt to dynamic environments and correct mistakes based on feedback. These data examples demonstrate the system's robustness in handling complex error scenarios, which are crucial for developing a reliable dialogue management system. The authors of the research paper present two illustrative examples of the self-correction mechanism in their proposed conversational AI assistant. In the first example, as demonstrated in Figure 9, the assistant recognizes that its prior call did not match the user's request, despite being successful. This triggers the assistant to reissue a corrected call, showcasing its ability to self-correct and adapt to the user's needs. This scenario highlights the importance of contextual understanding and post-call analysis in conversational AI systems. In the second example, shown in Figure 10, the authors illustrate an instance of single tools, where the assistant utilizes a single tool to accomplish a specific task. This example underscores the flexibility and versatility of the proposed assistant, which can adapt to various tasks and tools to provide effective support to users. The single tools scenario also enables the assistant to refine its understanding of the user's preferences and improve its performance over time. The paper explores the utilization of parallel tools in complex task environments, as exemplified in Figure 11. This figure demonstrates an advanced cognitive strategy employed by subjects to solve intricate problems more efficiently. The parallel tools approach is based on the concept of multitasking, where multiple tasks are executed simultaneously to reduce overall processing time and enhance productivity. The authors highlight the importance of understanding how humans utilize tools in parallel to achieve their goals, arguing that this ability to multitask with tools is a key aspect of human cognition and problem-solving capabilities. Figure 11 showcases a subject using two distinct tools, a hammer and a screwdriver, simultaneously to construct a piece of furniture. This parallel tools strategy allows the subject to complete the task faster than if they were to use each tool sequentially. The researchers also delve into the neural mechanisms underlying this parallel tools strategy, proposing that it involves the activation of multiple brain regions responsible for motor control, attention, and working memory. The coordination between these regions enables the subject to manage multiple tasks in parallel without significant cognitive overload. The paper further explores the potential applications of understanding parallel tools in various domains such as robotics, artificial intelligence, and human-computer interaction. By developing machines and systems that can mimic human multitasking abilities, researchers aim to create more efficient and adaptable technologies. In conclusion, the paper presents a comprehensive analysis of parallel tools as a fundamental aspect of human cognition and problem-solving, with significant implications for advancing our understanding of human behavior and developing more sophisticated artificial intelligence systems. In Figure 12, we illustrate the versatility of our proposed framework through a multi-tool use scenario, showcasing an agent's adaptability in tackling complex tasks. The top row displays the initial environment state, including the agent's starting position, tool locations, and the problem to be solved. The middle row highlights the agent's decision-making process, where it sequentially selects a hammer, screwdriver, and pliers to solve the problem. The bottom row presents the environment state after each tool application, demonstrating successful problem resolution. The key insight here is that the agent learns to prioritize tool selection based on task requirements and environmental dynamics. This is achieved via the integration of a task-oriented attention mechanism, focusing on relevant tools and objects, and a graph-based policy that captures tool-object interactions and task constraints. Mathematically, this is formulated as a Markov decision process, MDP, with the agent's policy represented as a graph neural network, GNN, trained using reinforcement learning to maximize cumulative reward while minimizing tool switches. The figure also underscores the importance of the graph-based policy in capturing causal relationships between tools and their environmental effects. By representing tool-object interactions as a graph, the agent can reason about action consequences and make informed tool selection decisions. Overall, Figure 12 demonstrates the effectiveness of our proposed framework in handling complex, multi-tool use scenarios and showcases the agent's adaptability to changing task requirements and environmental dynamics. The Math Comprehend Plus model, an advanced iteration of the original Math Comprehend model, is designed to enhance comprehension and generation capabilities for mathematical expressions by leveraging deep learning techniques. Figure 13 illustrates the model's processing of complex mathematical expressions, demonstrating its ability to understand context and structure, and generate accurate and contextually relevant mathematical problems. Math Comprehend Plus combines natural language processing and computer vision techniques to analyze and generate mathematical expressions, capturing both syntactic and semantic aspects of mathematics. This fusion enables the model to generate coherent and challenging math problems. The model is trained on a large dataset of diverse mathematical expressions, ranging from simple arithmetic operations to complex calculus and algebraic equations, allowing it to develop a robust understanding of mathematical concepts and their relationships. Incorporating real-time teacher feedback is crucial in fine-tuning the Math Comprehend Plus model, enabling it to adapt to different teaching styles and curricular requirements, and generate personalized math problems for students. However, the model still has limitations, including its inability to fully understand abstract mathematical concepts and its reliance on visual cues for problem generation. Future work should focus on addressing these limitations, potentially by integrating additional AI technologies or expanding the model's training dataset. Despite these limitations, Math Comprehend Plus has the potential to revolutionize math education through AI-driven problem generation, offering a promising solution for personalized and adaptive math learning. Directed Acyclic Graph, DAG, for question answering, DAGQA, is an extension of traditional question answering models, designed to improve efficiency and accuracy in answering complex questions. By leveraging the structure of a DAG, DAGQA represents relationships between entities, concepts, and context, capturing both local and global dependencies within the input text. This approach differs from traditional models that rely on sequential processing or simple graph-based methods. DAGQA is particularly effective in handling questions that require reasoning over multiple pieces of information, as it breaks down complex questions into sub-questions and identifies relevant information from the context using the DAG. Each node in the graph represents a piece of information or an entity, with edges signifying relationships between them. By traversing the graph, the model generates answers to the original question by combining the outputs of the sub-questions. This approach can significantly enhance the performance of question-answering systems, particularly when dealing with long, complex texts or questions that require multi-step reasoning. Future work includes integrating additional types of relationships into the DAG and exploring different learning objectives for optimizing the model's performance. In the concluding section of this research paper, The authors present a comprehensive analysis of the code contests framework's effectiveness in evaluating an AI agent's coding abilities. They highlight the importance of understanding and problem-solving skills as key components in determining an agent's proficiency. The paper introduces a novel task called problem parsing, which is designed to assess the agent's ability to comprehend and interpret complex coding problems. This task involves presenting the agent with a series of code snippets, each containing a specific problem or challenge that requires both understanding and problem-solving skills to solve. Figure 15 illustrates an example of the problem parsing task, showcasing how the agent is presented with a code snippet and must identify the underlying problem before proposing a solution. This task not only evaluates the agent's coding skills but also its capacity for critical thinking and analytical reasoning. The authors emphasize that the code contests framework offers a unique approach to AI evaluation by focusing on real-world coding challenges rather than theoretical or abstract problems. By doing so, it provides a more accurate representation of an AI agent's capabilities in practical coding scenarios. The paper discusses potential limitations and future work directions for the code contests framework, including the need for further development of the problem parsing task to include a wider range of coding problems and challenges, as well as exploring other evaluation metrics beyond accuracy and efficiency, such as creativity and adaptability. Overall, this research paper presents a significant contribution to the field of AI evaluation by introducing a novel framework that assesses an AI agent's coding skills in a practical and real-world context.